put force, Newton's second law, right? Force equals mass times acceleration equal to the gravitational equation. This is a no-no in physics. You can't get away with doing this in physics. That's the problem. Okay, you can't do this in physics. Okay, so let's show why you can't do this in physics. Give me a second here. Here you have Newton's second law is mass times acceleration. Okay, and the gravitational equation is the gravitational constant g. It's a constant, so we can almost forget about it. We're going to talk about the other stuff there. Mass, big mass, little mass over r squared. What is r squared? Again, they should never use r. It's called distance, okay, not r. And that's part of the problem. The fact that they use r should never be used, should be distance. Okay, so that's the first thing I'm going to clarify. Okay, and we'll find out why. Okay, and so what's the issue here? Well, the issue is that the equation on the left, mass times acceleration, has to do with distance traveled. What the guy is doing there, with the little guy there, right? He's pushing the box. Okay, he's pushing a box, and what the mathematicians are going to do, they're going to look at his starting point and his ending point, and they're going to say, well, how many meters, how many kilometers, how many miles? They want a number followed by units. Okay, that's what mathematics does, and mathematical physics uses the same equation, the same notion. They say, well, we don't care about the qualitative part, the fact that he pushed a box. We want to know how many meters, how long was the trip, okay? That's not what the gravitational equation is about. The gravitational equation, like the guys say, their little r, radius, which is wrong. It should be distance, okay? And again, you can't use radius because the Earth, you know, compared to the moon, its radius, the orbit of the moon, for those of you who believe that the moon goes around the Earth, it changes. It's elliptical and so on. So you can't use radius, because when you use radius, you're treating it as a circle. It's not a circle. You should use distance, okay? Because that equation gives you a single point. For that single point, you just look at that distance, okay? Not radius. And again, radius changes. And radius, the other problem with radius is that radius is calculated in meters and so on. And that's the other part of the problem. We're not going to be using units here. We're not going to be using numbers for anything, okay? We're going to look at this qualitatively. And we're saying that that equation on the left has to do with pushing, usually, right? Pushing a box from A to B. The other one has to do with the distance between A and B. And the mathematicians could never tell in the last 400 years, not a single mathematician picked up on this, that the distance, the separation between A and B is not the same thing as traveling from A to B. Why did they figure that out? Because in the religion of mathematics, distance, length, and distance traveled are synonyms. They don't care. They don't care about the qualitative difference between length and distance or distance traveled, because all they care is about a number. And the way they determine that number is by unrolling the measuring tape from A to B. No matter if it's separation, if it's distance traveled, or distance or length, right? They don't care. Because what they're going to do for distance, for length, for distance traveled is unroll the tip of the measuring tape, and they're going to count how many meters, how many kilometers, how many miles, or whatever. Okay, so this is the issue. Okay, so qualitatively, they're not the same, not in physics. So to put those two equations, one equal to another, they're comparing apples and oranges. Okay, let me get rid of this guy. So here we have the equation that mass times acceleration ends up being velocity squared over r, okay, for at any star that goes around. I'm not going to derive it. You can very quickly look up on Google. With at least high school level math, you can figure that out, okay? But acceleration is velocity squared over r, over the radius, okay? Okay, so again, we're saying those two equations are not the same. Let me get rid of this. Okay, so what's the issue with the stars? Okay, this is the issue. Here we have the equation that they come out of these two equations, right? One dynamic, which is the one on the left, the other one static, the one that's on the right, okay? And from that, they derive the equation at the bottom, which is the velocity squared is equal to the gravitational constant g. Again, it's a constant. We can almost omit that for the purposes of our discussion. We don't care about that if it's going to be a constant. We're concerned about the big M and the little r. What's the big M? Well, the big M is a big mass, for example, the sun, and the little m would be the earth. Or the big M would be the earth, and the little m would be the moon. And the same thing happens with a star. The galaxy, or the you can say the perimeter, the orbit of a given star, anything within that orbit, all the mass that you find in there, all the stars, that's going to be the big M, meaning the galaxy. So that would represent the mass of the galaxy. And the star that's on the outside going around the galaxy, that would be the little m, okay? What is the r? It's the distance between the center of the galaxy and the star, okay? And what they're saying is that velocity of that star going around the galaxy is related, the square of the velocity. We don't care about the square because we're interested in the qualitative aspects here. But yeah, the square of the velocity of that star going around the galaxy is equal to a ratio of big mass, in this case the galaxy, over the radius of the star, from the distance of the star from the center of the galaxy. Okay, so that's the story. Okay, now what's the problem with that? Well, it creates some problems for these people because here you have the situation. Okay, give me a second here. Okay, and what is it? Again, we have distance traveled is what you have embodied in that little velocity. Okay, that's what we have. That's the distance traveled. Okay, and what do you have in the other side? Well, you have something different. You have distance, meaning separation. And here we have a galaxy. There you have the radius of that star to the center of the galaxy. Okay, that's that little r there. Here we have another galaxy. Let me get it up here. And it's got a bigger radius, as you can see there. Okay, so one is a short radius, the other one is a long radius. That's what I'm showing there. If the radius increases, then you can see what it's going to do to the velocity. As the denominator becomes bigger and bigger, that velocity, what's going to happen to it? Well, it's become smaller and smaller. Okay, so the velocity of the stars on the outside should be slower and slower and slower. Okay, the farther you are, the longer the radius or the longer the distance between the center and the outside of the galaxy, velocity should be slower. So what's the problem with that? Well, the problem is that the chart that they built from observations of galaxies looks more like this. That the farther you are, instead of going slower, which is the expected there from the visible disk, instead of going slower, it goes faster. Or if anything, stays more or less the same. But never does it go slower. And you say, how can that possibly be? It violates the equation. Okay, the equation said that the farther out you are, the longer the distance, the longer the radius from the center of the galaxy to a star, the slower it should go. And so velocity should drop as a function of distance. And that's not what we see out there. So this is the problem. And so they had to address this problem because they saw it in all the galaxies. And you say, hold it, all the galaxies? How do we solve this problem? Okay, and mathematicians, they came to the rescue. They always save the day, okay? And so here we have our equation again. Let me show it to you. Let's start here again. Okay, there we have the equation, our two galaxies. And so what happens when we increase the radius? And there we go. Let's make it bigger. Whoop. And so now we have a bigger radius. Okay, so what happens? Well, velocity should shrink. So how did they fix this problem? What they did was they started putting some things in there. They started putting some mass. They said, what if we put more mass to compensate for the longer radius? So that way they can keep it constant, or if you put even more mass, you can even get it to go faster. So what they said is, we're missing some mass. That's all that the problem is. That's the only way they could think of that they could fix this. So they said, let's put some more mass. And what they said, but we don't see any mass there. So it must be dark. And they called it dark matter. So they said, okay, now I understand. There's mass out there. I can't see it. So we'll call it dark mass. And better yet, let's call it dark matter because it's got to be some kind of matter. Remember, matter is mass. Matter has mass. So what they did is essentially this. They sprinkled this dark matter on the outside of the galaxies to produce the necessary mass, okay? The mass that they needed for the equation to come out right. This is all about equations, okay? And so here you see the chart now. If you sprinkle a lot of kilograms out there, only out there, not inside the galaxy, then yeah, you can produce the result. It's like, This fixes the problem, doesn't it? We can't see the stuff that's out there. But if we sprinkle these kilograms out there, okay, then obviously, you can produce the effect, the necessary effect that matches what we observe. The equations now match what we observe, and we're just going to call it dark matter. And so what they did after that was say, okay, so we have our dark matter. Now what we do is we look for it.